Hi folks, so welcome to CSE 757. This lecture is an introduction that will take you through the focus and goals and learning objectives of this course. This course is on enterprise software engineering, and this first lecture is an introduction to enterprise software engineering. So to begin with, let's define this term, enterprise software engineering. Well, engineering is the branch of science and technology concerned with the design, building, and use of engines, machines, and structures. So when it comes to enterprise software engineering, the large-scale engines, machines, and structures that are going to be engineered are the large-scale software systems that run enterprises. And what are enterprises? Well, these are large organizations such as banks, insurance companies, think nationwide insurance, or branches of government, such as the Internal Revenue Service, or the City of Columbus. So given the above definition, here is the agenda for the lecture. First, what is an enterprise system? We have given you a basic definition above, but further, we want to try and give you an understanding of why an enterprise system is quite complex and why engineering it is difficult. Second, we want to show you what enterprise systems look like from several perspectives. Third, we will explain what they do, that is, the functions enterprise systems typically perform, and fourth, what are they trying to achieve from a business perspective. Fifth, we will classify the challenges that enterprise systems encounter, or rather the engineering of enterprise systems encounters. Finally, we will introduce how we can manage these challenges. And by the way, that's what most of this class will be about, methods to reason about and manage the challenges of engineering enterprise systems. Does that make sense? If so, let's go on. In order to explain the complexity of an enterprise system, we must first expand its definition. So here's how we're going to define an enterprise system. An enterprise system is A, the software and the underlying technology, B, the business processes that the software implements or supports, C, the organizational structure, and D, the people within that organizational structure who interact within the business and the customers who interact with the business to generate business value. In other words, an enterprise system isn't just the software, and engineering it requires you to understand this in a holistic manner. We will show several perspectives of an enterprise system next in order to give you an idea of what we mean. So let's keep going. The next few slides will show several different views of an enterprise system. This is not an exhaustive list of views by any means. Well, all we're saying is there are different ways to look at a system. It just depends upon where you, the observer, are coming from. That is, what your particular perspective is. So this diagram shows a typical enterprise system, and here are the points I want you to take away from this diagram. The first is that a typical enterprise system is not just one application, but really a collection of applications. Each of these applications being targeted towards a different stakeholder. So a stakeholder is somebody who might be an employee, might be a customer, could be a manager, basically the kinds of people who interact with the company. So coming back to the enterprise system, there are typically applications or groups of applications that are targeted towards specific stakeholders, and there are many stakeholders, so there are many applications. Ultimately, all these applications serve some aspect of the company, so there's really a connection or a relationship among these applications as well. This relationship might typically be of two kinds. The first kind is around shared data. So one application, such as the sales and delivery application, will have a notion of a customer. And then the inventory and supply chain application will also have a notion of a customer. At the sales and delivery side, the customer will be someone who buys something. At the inventory and supply applications, the customer will be somebody who receives something, who sent something, a product or something like that. Okay, so that's what we mean by shared data. And certainly all the applications will have some notion of the money that is earned, things like that. So this central database that we show in the middle is a conceptually centralized database. I didn't mean to imply with this application that there was an actual central database that all these applications worked off. What I'm really trying to say here is that there is this notion of enterprise data that's shared by all these applications. The second thing that these applications will share are processes. So there will be processes that begin at one application, go through other applications, and sort of end at another application. And once again, let's take the example of somebody buying something from this company. Okay, so that process of buying something, so it's known as the order to cash process. Okay, so you place an order, and ultimately you pay your cash, and then you receive the product. All right. Would begin at the sales applications, right? Would begin at a website where you would buy the thing, and then and then you'd make the purchase there. There might be an inventory management application that is told that this item has been bought and inventory should be reduced by a certain amount. And then there would be a shipping or a supply chain application that would then ship that product. So all these three applications are participating in one process. Okay, so keep this in mind that these different applications share or conceptually share data, and they also conceptually take part in common processes. All right. And then the last thing is that these different applications are targeted towards or geared towards multiple stakeholders. So there's not just one kind of business user, there's multiple kinds of business users. So now this diagram shows one of those applications, a prototypical application within that set of applications that make up the enterprise system. Okay, so typically this application will be architected as multiple layers. So the topmost layer will be a presentation layer. Here's where the user interacts with the application. Is able to provide input, is able to view output from the application. That's known as the presentation layer. The layer underneath that is usually called the business layer or the business logic layer. That's where the business operation actually takes place. Okay, so once again, think of an e-commerce application like Amazon. The web page is the presentation layer, and then when you click on buy the product, the business logic layer is the one that executes the transaction of buying. All right. Now, in order to execute that transaction of buying, the business logic layer has to call a bunch of services, and a typical service it will call is a database service. Okay, so in order to update something in inventory, or either add or delete, or add dollars to an account, or if the transaction happens to be the modification of an item, then the making the change to that item, something like that. But there are other services that this business layer might call as well. So there might be a remote system, for example, the warehouse system, which has to be told to ship a product, in which case it's going to call the service of the warehouse system. So keep in mind that this business logic layer will then turn around and call multiple services, a database service, a remote warehouse service, a remote credit card service, whatever it might be. And these services are implemented in what is known as the service layer. Now, these services will call functions, if you will, in the entities that provide those services. So there might be a database, there might be a web server that implements these web server services. There might be what is known as a message broker that sends these messages out. So those would make up the final or fourth layer of the enterprise system. So now that you've understood what kinds of new requirements these enterprise systems have to support, keep in mind that these enterprise systems have to evolve to support these new requirements. That is, you can't trash all the enterprise systems you have and then rebuild them to support these new kinds of demands. Okay, you've got to work with what you have and evolve them to what you need. Okay, so now this slide basically illustrates the complexity of doing that. So this is an example of a real enterprise system. This is a picture of a real enterprise system. You can see how complex, how many components there are and in how many complex ways these components are interconnected. This picture was derived by putting a crawler on one system and allowing it to spread like a worm to all the connecting components and to the components that connected those components and so on, and that then returned back a complete picture of that enterprise system. So this includes things like hardware components, operating systems, virtual machines, networking components, routers, things like that, applications. It's that kind of picture. Okay, so imagine taking a system that looks like this and modifying bits of it to be able to provide new requirements, new services. Okay, this picture illustrates in a nutshell the complexity of doing something like that. So what do enterprise systems do? Well, and for the moment speaking purely with respect to function, enterprise systems work with the information component of products and services. All products and services and processes have an information component. For example, a laptop has information about its components inside and the software on it. The information intensity of the products, processes, and services of an enterprise determine the impact its enterprise systems will have on that enterprise. For example, enterprise systems could automate business processes. Ideally, all business processes would be automated by enterprise systems, as computers can do repetitive work faster than humans. It allows the business to focus on human interactions, delivering value to its customers. It reduces the cost of operations for the enterprise, lowers its bottom line. Even processes that cannot be automated. For example, let's say there's a manual process by which somebody has got to walk to the back of the store, pick up an item, and bring it to the desk. Well, even a process like that could be automated. Even a process like that could not be automated, could be supported by an enterprise system. For example, the system could tell the person, the picker, where that item is on the shelf. So basically, it has helped by providing easy access to pertinent data for that process. Enterprise systems also provide business intelligence. Business intelligence is information about how the business is running and the efficiency of its processes. Who is buying its products? Where are they buying its products from? Ideally, an enterprise system can show where the business is inefficient by providing business intelligence on its operations, allowing the business to adapt and change that process. All of this functional stuff, that is what the system does, must be achieved while supporting key non-functional requirements. Enterprise systems must evolve with the business. If the business changes, you don't want the enterprise systems to be supporting the old business. For example, if they provide outdated business intelligence, the system does not provide any business value, and the system has cost money and has provided no return on the investment. Other key non-functional requirements like scalability, performance, etc., must be implemented or supported as well. Scalability is key because if the system is not scalable, the business cannot grow. Performance is key because if the system underperforms, the people using the system are essentially wasting their time. Usability allows non-technical business folks to easily access information and do their stuff within the enterprise system. Maintainability helps current and future IT employees to support the system better. In other words, not only is what the systems do important, it is also important how they do it. Having enterprise software systems meet functional and non-functional requirements is unfortunately only part of the battle. The bigger issue is one of business IT alignment, which is that the IT elements in an enterprise must align with the business aspects. Note that the IT elements that we're talking about are not just the systems, but the IT organization, its people, and its processes. This last is a point that IT folks have a hard time appreciating, probably because of their extreme technical bent. And actually can't blame them either. The IT technology is difficult enough to implement, so IT folks are focused around that and are really not thinking about the bigger picture. Without this business IT alignment, however, there is a poor use of resources and consequently poor results. Take the people issue, for example. Personal friction between IT and business professionals can often cause the requirements of a project to be not fully understood, resulting in projects that are either overly expensive or, in any case, not properly constructed. Ultimately, lack of alignment could cause the business to see IT as a necessary evil to be managed into being as cheap as possible. Instead, IT should really be a key to the success of the business. An aligned business IT relationship helps to prevent these kinds of problems from occurring. Business IT alignment challenges can be placed into four categories. First, people challenges around the culture of the people in the different departments or organizations within the enterprise. Process challenges that arise from the complex nature of software development. Third, technical challenges around enterprise systems. These technical challenges are unique to enterprise systems, and we will cover them later in this lecture. Environmental challenges that arise from the business environment in which the system operates. Take a look at the pictures on the slides. Yes, this is stereotypical, I admit that, but often so true. The straight-laced businessman wears a suit to the office, follows formal procedures for meetings, and works traditional hours from 9 to 5. The developer wears whatever he wants to the office, is gruff and doesn't interface well with the others, and works strange hours. Policies can help address these challenges. Commonly, IT departments raise their dress code to reflect the rest of the company. Hours are determined based on need. However, these needs are well communicated to the rest of the business so that they know when the IT folks are working. The IT workers become conversant in the language of the business so that they can explain IT issues and IT opportunities in business terms rather than in technological terms. Software is supposed to be infinitely changeable, right? Surely a business's agility shouldn't be held back by the software systems that support it. Wrong. There are many examples of where the business has been held back by the software. One example is right here at OSU. The story goes that our transition to semesters was held back because our enterprise systems were heavily customized to quarters and were very difficult to change to support semesters. One specific reason why IT holds back the business is that the highly structured software development processes, such as waterfall, that were traditionally followed by IT organizations, don't deal well with change. Hence the need for what are known as agile processes. There are technical challenges that are unique to enterprise systems and a result of their large scale and size and how these systems came into being. These unique technical challenges of enterprise software and systems essentially fall into two categories. Challenges due to the distributed and loosely coupled nature of enterprise software. These challenges include being able to manage distributed transactions, being able to manage distributed state, the issue with partial failures, that one piece of the system might fail silently without the other systems knowing about it. Having to manage concurrency across all the different systems, the components in the enterprise system. The second kind of challenges are the challenges due to the heterogeneity of the components of an enterprise system. Heterogeneity in who uses it. The users of the system consist of different types of people in different locations with different expertise. The different systems that make up an enterprise system could each be built using different types of technologies. So an enterprise might have mainframes that need to interact with Linux, Windows, or Apple workstations. There is heterogeneity in hardware, operating systems, implementation languages, technology frameworks, applications built in .NET having to interact with applications built with enterprise Java. This causes problems in, for example, integration compatibility and correctness. Basically, the different systems, the different components in an enterprise system have to work well together, have to be compatible in terms of data exchange and so on. And then ultimately that integration has to work correctly to fulfill a larger business process. The second kind of problem is in integrated management. All these components are different, being able to manage them as a whole, being able to monitor them as a whole, upgrade them as a whole, all these kinds of things are issues. The key point here is that these technical challenges are not created by choice, so they can't be managed away, but are a byproduct of natural evolution of the business and the enterprise system in response to the business evolving, or just because the technology itself also evolves. In other words, these technical challenges cannot be managed away or designed away, they have to be dealt with. Environmental challenges are those that affect the business climate of the enterprise. For example, an environmental challenge is increased competition due to globalization. Another environmental challenge is where an enterprise's standard products, the ones it used to make significant profit from, have become commoditized and can no longer fetch the prices they once used to. Just think about long distance service. 20 years ago, the telecom companies made a lot of money from plain old long distance service. Now, with IP telephony, long distance calling is essentially free. Because of the commoditization of most products, a significant global trend that is affecting large companies today is a move towards services. In fact, most developed countries are moving to a service-based economy because citizens can get standard products much more cheaply from countries like India and China. For these products, developed world companies cannot compete on price. Thus, companies in the developed world are increasing the component of services in their offerings. For example, Nationwide used to be a pure insurance company selling standard home, auto, and life insurance policies, all mostly through agents. It used to be able to charge a good amount for these policies, but now it has new competitors, such as Progressive Insurance, who are able to sell these standard policies much more cheaply by simply selling over the web and eliminating the cost of the agent. In order to compete with Progressive, Nationwide is now trying to provide better customer service as well as custom insurance products that are tailored specifically to you. Essentially, it is offering insurance as a service. Another way to think about this trend, a more high-level way or more general way to think about this trend, is that companies are being forced to move away from the routine products that they used to offer to services which are essentially non-routine products. Note now that computing has been very good so far in the automation of routine things. I leave you with a challenge. Can you think of how computing might help with the non-routine? Now that we know about people, technology, process, and environmental challenges, how do we address them? With some study and thought, we have found that these challenges fall into patterns. From these patterns, we can extrapolate general ways to solve these problems. These general ways of solving these problems are called frameworks. Frameworks help reduce complex challenges to understandable problems that we can then solve. Frameworks then guide us in how to find solutions to these problems and also help in evaluating and measuring the performance or the fit of the solution that we come up with. In the next slides, we will give you common examples of frameworks. Our first framework example is from physics. The equations of motion make up a framework for understanding how rigid bodies move. Basically, they model, or more precisely mathematically model, the relationships that can both describe and predict the motion of a particle under the influence of a force and as a function of time. Our next framework example is from business. A balance sheet, which is used in business and accounting to tally up the income and expenses of a business, is another example of a framework. This framework, this balance sheet, gives us a standardized way of checking the health of a business. Note that without this framework, the task of figuring out whether the company was healthy or not would be much harder. Essentially, the framework removes much of the complexity of the task. Now to a framework that is more relevant to this course and to software engineering. The Universal Modeling Language, or UML, is a systems modeling framework. It has a language of symbols that have a standard agreed upon meaning. UML allows us to capture a system and its relationships more precisely so that knowledge about that system can be shared with others. That's pretty much it regarding the content of this course. We do have one more topic that we'd like to cover with you, and that is how we are going to evaluate whether this course did what it was supposed to. Guess what? We're going to do this through an evaluation framework. The first part of this framework consists of learning outcomes, which you can think of as the measurable expectations of what you should have learned from this course. At the end of this course, we expect you to be, first, familiar with what enterprise systems are. In other words, if someone, your instructor, your mom, the man on the street, Willis, says, "Dude, what's an enterprise system?" you should be able to snap off an answer in a polite yet precise manner. Secondly, be familiar with the architecture of enterprise systems. In other words, you should be able to describe at a high level, because that's what architecture is, the components of an enterprise system and how they are connected or related. Thirdly, be familiar with the functional and non-functional requirements that enterprise systems are expected to meet. In other words, both the what and the how of enterprise systems. Fourthly, be familiar with the challenges facing enterprise systems. We talked about those, remember? People, process, technical, and environmental challenges. Finally, since you're all engineers and you should be very competent in thinking systematically, we expect you to be able to apply the frameworks in this course in a competent manner. Which leads us to the final learning outcome. Be competent with using frameworks for enterprise software engineering. We expect you to be able to systematically figure out how to engineer an enterprise system through the use of the frameworks taught in this class. Finally, note that the above are the learning outcomes for the course. The learning outcomes from this lecture come next. Having told you what you're supposed to learn, we are now going to tell you how we are going to evaluate your learning. We're nothing if not consistent. We will be using a framework here also, a framework known as Kirkpatrick's 4 levels of evaluation. You can think of this framework as a pyramid. At the lowest level is your reaction. This is a measure of how participants, such as you, have reacted to the instruction. We will determine this through the use of the SEIs at the end of the quarter and by measuring class participation throughout. The next level is recall. This measures what you have learned from the instruction. Recall will be measured through the weekly quizzes and the final exam. Third, we have application. Application is very aptly named because it measures what you're applying. It measures whether you're applying what you have learned in practice. We will measure this via the course project. We will also, if you take a capstone course after this one, measure your level of application during the capstone. And finally, there is transfer. This is the highest level of learning where we measure your ability to customize the techniques and frameworks you learned in this class in non-standard ways, in ways that we have not taught you to affect better performance at your work or even organizational change. This too will be measured, but in a preliminary manner through the capstone course after this class. And we will be very appreciative if after you graduate and you are hacking your way through professional life, and I mean that in the best way possible, if you drop us a line or two of feedback on how this course affected the way that you worked. And so finally, we will recap what we learned in this lecture, or at least what we presented in this lecture. We defined what an enterprise system was, what an enterprise system does, and what an enterprise system is trying to achieve for the business. We listed 4 types of challenges faced in engineering enterprise systems and explained what kinds of tools we were going to give you through this course to address these challenges. Finally, in order to measure the effectiveness of this course, we described how we were going to measure your learning. And this brings us to the end of this lecture. Hopefully you took good notes, and please come prepared with questions for the next class.